There are acids and bases. And acids usually start with an H and they produce H plus when they dissociate. And bases usually have an OH attached on the end and they produce OH minus hydroxide ion. Now, you have to know whether something is strong, which means it dissociates completely, or if it's a weak electrolyte. Electrolyte being something that produces ions. And there are millions and millions of acids which produce H+. But there are only 7 strong ones. We have hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric. And these are the only ones that dissociate completely into ions. Now, the way to know if something is strong is you have to memorize this list. And if it's not on this list of 7 strong acids, then it must be weak. And so it's an exclusive sort of definition in the sense of if you know it's not strong, then it must be weak. Now, the strong bases are the alkali metals, and it's all of the alkali metals with hydroxide. And the common ones are lithium hydroxide, sodium hydroxide, and potassium hydroxide. And then you have what are called the heavy alkali earth metals. If you look down the periodic table at the alkali earth metals, you'll see that calcium starts at row 4, and anything from that row on down is considered a heavy metal. And so we have calcium hydroxide, strontium hydroxide, and barium hydroxide. Now, when acids dissociate, they produce H+, and it goes like this. So if you have HCl, hydrochloric acid, when it dissociates in water, it's going to produce the H+, and the OH, and the Cl minus. And we can do others like HBr, H plus Br minus. Now, if it has more than one H in the front, let's say like sulfuric acid, it will actually produce one at a time an H plus. So the first H plus comes off and you have H plus the bisulfate ion that's left over. And that's the strong acid. And then that will dissociate even further to produce the second proton, which is what an H plus is called. And now you have the sulfate ion. Overall, many times we'll write this like this. We say H2SO4, sulfuric acid, will dissociate into 2 hydroniums or protons plus the sulfate ion. And we can also say, let's say for phosphoric acid, H3PO4, those hydrogens come off one at a time, just like with the sulfuric acid, but we can write down that it is 3 H pluses that come off plus the phosphate ion. And so when acids dissociate, this is what you get. You get the H plus, a proton, plus whatever the polyatomic ion or element anion that comes off as well. And so it's the H plus that's going to actually be doing the reacting. The chloride, the bromide, the sulfate, the phosphate, those are there predominantly for charge balance. And so when a base dissociates, the hydroxide comes off. So we have, say, sodium hydroxide. It's going to produce the sodium cation plus the hydroxide. And just like with the acids, if you have more than one of the hydroxide, well, that 2 in the parentheses means you come off with 2 hydroxides. And that's important because you don't want to be writing down that you have this situation. This is bad. I see this all the time where people will say OH2 minus. And that's not real. That's not that. These guys come off one at a time, those hydroxides. So that's what's happening when we have acids and bases dissociate in water. And of course, everything is aqueous at this point. Now, what we have to be able to do is to react acids and bases in neutralization reactions. So we're going to do acid-base neutralization. Now, the key to acid-base neutralization is that H plus, which comes from the acid, reacts with OH minus, which comes from the base, to make water. And this is the key. This is also the net reaction for all acids and bases. Okay, that's the net reaction. Now, what you have to do is balancing acid-base neutralization reactions is actually pretty straightforward if you look at it this way, which is you have HCl plus, let's say, calcium hydroxide, and I want to know what happens. Well, the product of all acid-base neutralization reactions is going to be water plus its salt. But the easiest way to balance these equations is we take a look at how many of the H pluses are we going to get and how many of the OH minuses are we going to get. And if you see over here, we're going to get 2 hydroxides, which means we're producing 2 hydroxides. But for this to be balanced, we also have to have 2 H pluses, which means we have to put a 2 in front of the HCl. Now on the left-hand side, we have the correct number of the acid and we have the correct number of the base. We have 2 of the hydrochloric and we have 1 of the calcium hydroxide. Hydrochloric is going to produce 2 H pluses and the calcium is going to produce 2 OH minuses, which means that we're going to be balanced. We have to say that we're producing 2 waters. Now, we still have the calcium and the chloride. And there's 1 calcium on the left, so we put 1 calcium on the right. And now I have 2 chlorides, and so I have 2 chlorides on the right. And now this equation is balanced. Also, this is also charge balanced, the calcium chloride. And remember, we always have to have the net charge equal to 0. And so this is calcium 2 plus, and each one of those chlorides was -1. And to get the calcium chloride, we would have to cross the charges since they're not equal to 0. And of course, what does that mean? That means the 2 comes down on the chloride and the 1 comes down on the calcium. So balancing acid-base neutralizations is actually pretty straightforward once you realize that the key to it is that the hydrogens, the H pluses, have to equal the hydroxides, the OH minus, and you produce a water. And so if you have 1 of each, you produce 1 water. If you have 2 of each, you produce 2 waters, and so forth. And then let's not forget that you also have to take care of the resulting salt. So the result of any acid-base reaction, the products, is water plus a salt. Let's do another example where we're going to take advantage of the fact that the H plus and OH minus have to be equal. And let's say that we had, say, H3PO4 this time, which is phosphoric acid, plus sodium hydroxide, which is a base. And I want to know, what am I going to get? Well, once again, our focus should be on how many H pluses are you going to produce and how many OH minuses are you going to produce. And we're going to produce 3 H pluses off of the phosphoric acid and 1 off of each sodium hydroxide. So I need to put 3 so that I have 3 H pluses and 3 OH minuses, which means we're going to have 3 waters. Now, let's not forget about the salt part. because we still have to balance the equation. And I see that I have 3 sodiums to go with that phosphate. And so we say 3 sodiums to go with that phosphate. And even if you didn't do it that way, if you started out with, say, sodium and the phosphate and just balance the ions, because the overall charge has to equal 0, you'd cross those charges and you'd still come up with the sodium phosphate. So that's how you balance acid-base neutralization reactions. And of course, everything up here is aqueous as well. Now, the key skill that we need to be able to do is calculations involving acid-base neutralization. So let's go ahead and work through one. So let's say that we have the phosphoric acid, which we just did, plus the 3 sodium hydroxides going to 3 waters and the sodium phosphate. And we're giving the concentrations in molarity, and a reminder, molarity is moles per liter of solution. And we want to know, well, how much would it take to neutralize one or the other? So let's say if we're told, we want to know how many milliliters of 0.318 molar sodium hydroxide to neutralize say 29.69 milliliters of 0.218 molar phosphoric acid, H3PO4. Okay, now first off, we have to have a balanced equation. And the one thing that we always have to be careful about is we're always going to need the mole ratio between the 2 things that are reacting. And we look up there at the balanced equation, and we're looking for sodium hydroxide and the phosphoric acid. And I see the phosphoric acid, there's an implied 1, and I have a 3 in front of the sodium hydroxide. So I know that I'm going to need the mole ratio between the 2, and so I'm going to say 3 mole sodium hydroxide for every 1 mole phosphoric acid. And this is critical that we have the mole ratio between the 2, because if we don't, we're going to be off by a factor of 3. Okay. Now, the next step to doing these is go ahead and take anywhere where you see molarity, let me change colors here, and just go ahead and copy it down as moles per liter. This allows you to write it as a conversion. So I'm going to write the sodium hydroxide down as 0.318 mole sodium hydroxide for every liter of sodium hydroxide solution. This allows us to treat molarity as a conversion factor. And we have another molarity over here, and I'm going to go ahead and just copy that down as 0.218 mole phosphoric acid for every liter phosphoric acid. And so we now have 3 conversions that we can use for our equation. And we have a given, or measured, is our 29.69 milliliters. So we have all the pieces to set this up as a conversion factor, and now we're done with the problem itself, with the words, and we can go ahead and set this up. And so we always do this. We draw a line and draw another line. Start with our measured number, and that's the 29.69 milliliters of phosphoric acid solution. Okay. Now, I can't use milliliters like it is. And so what I can do is go ahead and I can either set this up so that we have milliliters to liters, or I could recognize that this is actually point. We move the decimal place over 3 times. This is 0.969 liters. Generally, you want to work in liters. So we're going to go ahead and copy that down as liters. That way I can use my molarity of the phosphoric acid. And I look over there and I see the molarity of the phosphoric acid, and it is 0.218 mole phosphoric acid for every liter of the phosphoric acid solution. And so that allows us, when we use molarity as a conversion factor, that allows us to cancel the units, and that leaves us with moles phosphoric acid. Now, if we need to put a check mark, and so now we go ahead and we're looking for moles phosphoric acid, and that's in our mole ratio, and so we'll leave that like it is and not flip it over. And so we copy that down. 3 moles sodium hydroxide for every 1 mole H3O P4, which is phosphoric acid, and we've used that as well. And then finally, we have the molarity for the sodium hydroxide, and we're going to have to flip that over to get mole sodium hydroxide on the bottom. So we say liters sodium hydroxide, moles, we need to put the units in, 0.318 mole sodium hydroxide, and that will get us liters. And then we can take our answer in liters and move the decimal point back over to get milliliters for our answer. So let's put this in our calculator, 0.02969 times 0.218 times 3 divided by 0.318, and I get 0.061 liters, 0.0611 liters, which is 61.1 milliliters. And so that's milliliters of sodium, of the 0.318 molar sodium hydroxide. And there you go. So now I have the milliliters of sodium hydroxide to do this problem. Okay, let's do one more example. All right, so let's start with a balanced equation. So how about we have HCl plus, let's see, who are we going to use? Let's go with magnesium hydroxide. And of course, we're going to get water plus the salt, which would be magnesium chloride. And let's go ahead and balance it. And it looks like we're going to need 2 HCl's, and we'll get 2 waters to go with our magnesium hydroxide. And so let's say, how many milliliters of 0.100 molar HCl to neutralize 14.97 milliliters of 0.300 molar magnesium hydroxide. Okay, so the same idea applies here. First off, you do need the mole ratio between the two things that are reacting, and we'll go ahead and write down the mole ratio. The mole ratio is 2 mole HCl for every 1 mole magnesium hydroxide. And then let's go ahead and just copy down what we have in the form of the molarities. Let's just copy them down in the forms of moles per liter. And so that would be 0.100 mole hydrochloric acid for every liter of hydrochloric acid solution. And then the other molarity is 0.300 mole magnesium hydroxide for every liter of magnesium hydroxide. And so, as I said before, this allows us to treat the molarities as conversion factors. And so now we're ready to set up our equation. And I'm going to go ahead, and this time I'm not going to put the milliliters into liters. I'm going to leave them as milliliters and convert them to liters in my setup, just to show you that there are two ways of doing this. It's going to be a longer line. And we start with our 14.97 milliliters of magnesium hydroxide. And of course, we're going to have to convert that to liters. And so we say liters of magnesium hydroxide solution is 1,000 milliliters of the magnesium hydroxide solution. And that'll get us in liters. And we could have done that ahead of time. But let's go ahead and put this in here so we're converting to liters. And now we can use our molarity of our magnesium hydroxide. And that's moles magnesium hydroxide for every liter of magnesium hydroxide. And so far, everything is canceling like it should. We have milliliters canceling with milliliters, liters of magnesium hydroxide, liters of magnesium hydroxide. If we were to stop here, we would have the moles of magnesium hydroxide. And now we need the mole ratio to cancel out the moles of magnesium hydroxide. And so we have 2 mole HCl, hydrochloric acid, for every 1 mole magnesium hydroxide. And then finally, we use our molarity of the hydrochloric acid to get the liters. We're going to have to flip it over. And then we'll go ahead and convert the liters into milliliters. And that is liters of hydrochloric acid solution for every 0.100 mole hydrochloric acid. And if we stop there, we'll have liters. But let's go ahead and convert it to milliliters for every liter, and we're done. And all it's left to do now is to put this into our calculator, and we will have our answer. So we have 14.97 times 0.3 times 2 times 1,000 divided by parentheses 1,000 times 0.1 close parentheses, and I get 89.8 milliliters. And that would be of the hydrochloric acid solution, which is 0.100 molar. And that's how you do it. That's how you do acid-base neutralizations. The key points in here is make sure that you have the balanced equation, that you have the mole ratio from that balanced equation. Turn all your molarities into moles over liters, and then starting with your measured number, make sure everything matches up and cancels as you go across. And so sure enough, moles, 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 liters, liters. And make sure everything cancels as you go across. And that's how you do that.